let's look at some stuff. Let's graph like the only 3D shape I'm really good at graphing. So let's draw the saddle. Let's graph the saddle f of x, y equal to, what do we got here? Y squared minus x squared. And we're going to do some stuff. So let's see here. I don't really want the coordinate. Let me draw. Here's my positive z-axis, and here's my x-axis coming at us. I might want this data. Okay. So let's see. If I was graphing z equal to y squared minus x squared, I would graph in the yz plane. So let x equal 0, I'd graph z equal to y squared, which looks like this. Let's do a decent job of this. I do want to make this look good. I got too big there. That's all right. And then in the xz plane, I'm going to have y equal to 0, so z equal to negative x squared. So it's going to be a downward opening parabola that way. Is your screen pinned? It is pinned. Usually I say something, I know, but I remember to do it. So yes, thank you for asking. So it's going to look like this. I feel like this one I never really do a great job of getting. Okay, and then the way I kind of imagine this looking like, right? So like this way we have parabolas going downward and parabolas going outward. So we kind of have this. That. Obviously, it's not the whole thing, but I think that does a pretty good job of kind of seeing what the thing looks like. And so if you want, you could draw some level curves in various directions, but I don't think we really need to do that. Really, I just kind of want to draw because the picture I can actually draw. That's not the whole reason, but one of the reasons. So let's talk about finding a few normal things. So not, well, actually pun not intended, but it's a good pun. Let's find the gradient, which is a normal, right? It's a perpendicular. Okay, yeah. So let's find the gradient at the point 4, 5. All right, so the gradient, right? It's going to be, the gradient is a derivative. Well, this, but it's a vector. It's the partial in the x direction, partial in the y direction. That's going to be, so the partial in the x direction is negative 2x, partial in the y direction is 2y, evaluated at 4, 5. So we are looking at, let's see, negative 8, positive 10. So there's our gradient. And I should point out, let's see, can I plot this point? Maybe. So if I plug in 4 for x and 5 for y. So 4 for x, 5 for y. We're kind of like, maybe we're like right there on the surface, right? We've gone over 4, or actually we go out 4. Right, we've kind of hit this point on the surface. Like that. So right, that's where we're on the surface. And we're asking is, okay, at that point on the surface, what is the direction? What's the gradient again? It's the direction of steepest ascent. So from this point, and maybe it'll be good to draw a level curve here. So I'm going to erase all this stuff because I don't think we really need it. Right? We got the gradient. It's negative 8, 10. And so at that point, let's draw the level curve, which is again the curve in the xy plane, except we're setting z equal to whatever the height is there, which is going to be 9. So if I want to draw z equal to 9, so 9 equal to y squared minus x squared, it's a hyperbola with y-intercepts 3 and negative 3. Counts like this. And we're at the point, I said 4, 5, right? Yeah, x is 4, y is 5. So we move down to 4 up 5. So we're like right there. And what we're saying is at that point, right, this point here is the same as that point there. So at this point, if you move in the direction of negative 8, positive 10, so sorry, I know we're kind of, if we're essentially moving this way and a little more that way, not quite, maybe like that. And that's the direction. Right, that's the direction, meaning we're going to be traveling up the surface. That's going to be the direction of steepest descent, which seems reasonable, right? It looks like if you traveled, I know it's, again, it's hard to always see the perspective, right? But if we traveled that way, right, kind of not perfectly left to right, but kind of back and left to right, we would be going in the direction of the steepest part of the curve. Cool. Other questions we can ask? What is the slope of the surface if we travel in this direction? Okay, well, we know if we're traveling in the direction of the gradient, the slope is the steepest it can be, and the steepest the slope can be is the magnitude of the gradient. So that's going to be the magnitude of the gradient at the point 4, 5. I know it looks kind of funky. That's just going to be the magnitude of this vector, which is going to be the square root of negative 8 squared plus 10 squared, which is the square root of 164, which is a little less than 13. Okay, so it's got a steepness of 13, or a slope of 13. All right, let's look at some other stuff. So let's now, at this point, think about what the tangent plane might look like. So my drawing skills are probably going to start to devolve here. The idea is we're basically saying, okay, I want to know. So that picture looks funky. Sorry, I'm looking at this picture, and it looks like the gradient is going in the wrong direction. Or maybe I'm just having a hard time seeing it. Oh. Well, it should be. Okay, I see. I get it. Yeah. Sorry, it's not the so something's different. But okay, yeah. Okay, so let's say we want to find the equation of tangent plane. And this is where we have to kind of adjust our way of thinking. So we learned before, right, that we can find the equation of a tangent plane by using the coefficients of the normal vector, right? If you knew, and I'm gonna try and draw the plane here. This is. Let me try using a different color. Maybe it'll make it. It might be better. It might be worse. Sorry. So right here, right, there's a little like. Here's my plane that's tangent to the surface at that point, and shooting out of it is the normal vector. And if we knew the coefficients of the normal vector at that point, which is the point of 5, 4, 9, right? So if we knew the coefficients of the normal vector, we could find the equation of the plane, because the normal vector is perpendicular to the plane. And so we would say, like, whatever the coefficients are times x, y, and z equal to whatever the constant is. Okay, this is where things get a little bit heavy. What we're going to do is we're going to say, we're going to take our equation, f of x comma y comma z equal to y squared minus x squared. Sorry, f of x y, not f of x y z. Apologies. We're going to call this z, as we often think of it as. And we're going to rewrite this as z equal to y squared minus x squared. And then we're going to isolate or bring all the variables to one side. So we're going to say like y squared minus x squared minus z equals 0. That's going to be our new equation. And we're going to call this function capital F of x comma y comma z. All right. Now this is where I think things are a little bit weird. For a 3D surface, if we're talking about the gradient at a point, you're talking about what direction in kind of in the xy plane, what direction you could travel that would make you go up the steepest slope. But now what we're going to do is we're going to say, well, we're going to think of our function as this function of 3 variables, and instead of thinking about level curves, right, where we're saying, and I know I keep erasing my pictures, right? If we were thinking about the level curve, and basically the point of the level curve, the direction that's going to be kind of the direction of the gradient is the direction that's perpendicular to the level curve, and that's going to be the direction that makes you go up in the steepest direction. Sorry, the words are failing me here. But the thing I'm trying to say in the longest way possible is that the gradient is perpendicular to the level curve, right? If your level curves are like your topographical map, right? The way you go up the steepest is by crossing the level curves the fastest, because those represent different elevations. So now here's kind of the thing that's bizarre. Maybe weird. What we're going to do is we're going to think of not level curves, but level surfaces. So this surface is one level surface where the function of x, y, and z is equal to 0. And then I'm going to maybe draw just a tiny smidgen of it. We could think of like the next level curve, level surface, to be the same thing, but now it's where it's equal to 1. So basically, you shift the entire surface up to 1. So you'd have, and it's going to be kind of bizarre, right? It's kind of the idea. So the idea here is that you've got these level surfaces. What we're going to do is we're going to find this normal vector by finding the gradient to the surface. But the gradient to a level curve is perpendicular. Sorry, the gradient to a surface is perpendicular to the level curve. So the gradient to the vector that's perpendicular to the level surfaces is the gradient. Maybe that's a lot of explanation. Maybe it's not the best, but the idea here is that, let's say over here, for a 2-dimensional level curve, we have that the gradient of f is perpendicular to the level curve, where the surface is given by f of x comma y equal to, or I should say, right, z equal to sum f of x, y. Whereas for a 3D level surface, the idea is that the gradient of your capital F is going to be perpendicular to the level surface. Where capital F is a function of x, y, and z. Hopefully that doesn't seem too terrible. So that's maybe a lot of explanation for what we're going to say now is that we're going to take our function there and find the gradient of it. That's not terrible. The gradient of capital F is, let's see, it's going to be negative 2x, positive 2y, negative 1. And then we're going to plug in the point. So at the point 5, 4, 9, we're going to get, let's see, -10, +8, -1. So now to find the equation of the tangent plane, well, we're going to use those coefficients for x, y, and z. So the equation of our tangent plane is going to be, and I think the easiest way to do it is to do it this way. It's going to be -10 times x minus 5 plus 8 times y minus 4 plus, I'm out of room, z times, sorry, plus -1 times z minus 9 equal to 0. This plane goes through the point 5, 4, 9, and it has the normal vector -10, 8, -1, which is exactly how the plane is described. So the more compressed explanation here is that for any kind of surface where you've got, where maybe you can't just solve for z as a function of x and y, but you have some surface described in terms of variables x, y, and z, this is how you're going to find the tangent plane to a point. You're going to find the gradient at the point. That's going to be your normal vector to the surface. And then you're going to use that normal vector as your coefficients and then use your point to find the equation. So it's actually not a terrible calculation. Let's do a couple more examples. The explanation, I think, feels a little strange. That's all right. So let's look at this one. Let's look at, I want to find the equation of the plane tangent to, what do we got here? The sphere, x squared plus y squared plus z squared equal to 9, which is a sphere of radius 3, at the point 2, 1, 2. Okay. As far as finding your capital F function here, you can basically ignore any constants. So you could say capital F of x, y, z is x squared plus y squared plus z squared. And we're looking at where it's equal to 9. Or you could alternatively say capital F of x, y, z is, I'm like, where'd that good red pen go? I think it's literally right in front of me. There we go. Is x squared plus y squared plus z squared minus 9. And we're looking at where it's equal to 0. But again, right, this is a level surface, right? There are many, many different level surfaces we could find. We're just trying to find the thing that's perpendicular to our level surface. Either way, whether it's this one or this one, the addition or subtraction of a constant isn't going to affect the gradient at all. Both of these capital F's are going to have the same gradient. It's going to be 2x, 2y, 2z. Right? Each of the partials aren't affected by that constant. And so then the gradient, or the normal vector at the point 2, 1, 2 is going to be 4, 2, 4. And then the equation of our plane. So there's two ways you can do this. One way, kind of the more general way, is to say it's going to be 4 times x minus 2 plus 1 times, sorry, not 1, plus 2 times y minus 1 plus 4 times z minus 2 equal to 0. That's a perfectly legit way to do it. The other way you can do it is to say, well, I know these are my coefficients of x, y, and z. So you're going to get 4x plus 2y plus 4z equal to some constant d. And then you plug in this point to find the constant d. So that 8 plus 2 plus 8 equals d. So that's going to be 18. So my equation is 4x plus 2y plus 4z equals 18. Or you can divide everything by 2, right? Because you can change an equation by multiplying or dividing by a constant. and say that I should say really not changing the equation. 2x plus y plus 2z equal to 9. That's the same as this. It's just that it looks a little different. So let me go to this other question that somebody had asked. Oh, darn it. Did they literally not write down the equation? Yeah, I did. Okay, right here. So the thing about a tangent plane is it is the linearization of a function at a particular point. So let's kind of let's look here. So here's the question that somebody asked, and they said the first part was perfectly fine. I'm still going to go with that. So let's say we've got the function f of xy equal to xy squared plus y times sine of x plus pi over 2. And we want to find the linear approximation of the point 0, 2. So the linear approximation at 0, 2. AKA the equation of the tangent plane at xy equals 0, 2. And well, I should point out, specifically when you're talking about a linearization of a function of two variables, yeah, you're finding the equation of the tangent plane, but then you're specifically solving for z. So there's a couple ways you could go here. I want to kind of keep it in the same context of what we've been doing. So I'm going to go ahead and say, I'm going to go ahead and replace my function with z. This might not be, I don't know, I feel like this is straightforward. So I'm going to say, I've got, this is z. And then I'm going to say that this plus this minus z, so xy squared plus y times sine of x plus pi over 2 minus z, that is my function of x, y, and z. So now I'm going to find the gradient, which is going to be, let's see, so partial with respect to x, it's going to be a y squared plus a y times cosine of x plus pi over 2. That's, sorry, this is my first, I'm writing this kind of terribly. Too much, a little more room here. So my gradient is going to be, the first coordinate is going to be the partial with respect to x, so y squared plus y times cosine of x plus pi over 2. And then my partial with respect to x is going to, sorry, with respect to y is going to be 2xy plus sine of x plus pi over 2, comma, -1. If you're doing this kind of thing and you've already got your function as a function of x and y, when you're finding this gradient here, it's always going to have a -1 for the z part, for the j part if you want. So then the equation, I should say, and then I want to evaluate this at 0, 2. So my gradient evaluated at 0, 2, I should also see what z is. So if x is 0 and y is 2, then my function z is going to be, let's see, that's going to be 0 plus x is 0, y is 2. That's going to be 2 sine of pi over 2, which is 1, so that's going to equal 2. So z is also 2. So now it's going to equal, let's see. So I'm going to get 4 plus 2 times cosine of 0 plus pi over 2 is cosine of pi over 2, which is 0. So I'm going to get 4. 2 times x times y is going to be 0. Sine of 0 plus pi over 2 is going to be 1. -1. So there is my gradient. And that's good. So then I can find the equation of the tangent plane. The equation of the tangent plane is going to be 4x plus 1y minus 1z equal to some constant. And the constant is going to be whatever I get when I plug in the point 0, 2, 2. So 0 plus 2 minus 2 equals the constant. It ends up being 0 here. So the equation of my tangent plane is 4x plus y minus z equals 0. We're solving for z equal to 4x plus y. So this is my linearization. I feel like I might have made a mistake somewhere, a small one at the end here that I'm kind of, something feels slightly wrong. I just want to make, no, I guess that's fine. Yeah, that's all right. When I plug in my point, 0 for x and 2 for y, I do end up getting 2 for z, which is what I saw here. Okay, that seems okay. So there's my linearization. And then, yeah. So then they ask us, and this is something I've never, at least don't recall ever seeing, what's an upper bound on the error for the difference between the linearization and the function? So they're asking us, and there's a little bit more qualification there, sorry. We're being asked, what's the upper bound on the error, that's written here, sorry, which is equal to the absolute value of the difference between the linearization and the function, which in this particular case is, so the linearization, which we just found to be 4x plus y minus the function itself, which is this hot mess here. And we're given a little bit more to say about that, sorry. So it's about on this error if the absolute value of x is less than 0.1, and the absolute value of y minus 2 is less than 0.1 as well. That seems totally out of left field to me. So here's the idea, right? We're basically saying x is close to 0, y is close to 2, which makes sense because we did the linearization at the point 0, 2. Sorry, so this function here is supposed to be a good, or so this linearization here is a good approximation of this function here near the point we linearized at, which was at the point 0, 2. So that's why we need this kind of qualification that, oh yeah, we are close to 0, 2. So here's the formula. This is in the book. It's in section 14.6. The justification of it is later on in section 14.9 or 14.10. I don't think you need to know the justification of it, but here is the formula. So the formula, I wrote it down. So the error is less than or equal to 1/2 of n, which we'll talk about in a moment, of x minus x naught plus y minus y naught in absolute value squared, where m is the upper bound of the second partial fxx in absolute value, fyy in absolute value, and the mixed partial fxy on the interval. Oh, sorry. Yeah. On the region being described. Okay, so what do they mean with region? Well, that's what this is describing here. So what we're saying here is that, yeah, we're looking at the point 0, 2. And we're saying you can go left or right 0.1. So I'm going to say here's 0.1, here's negative 0.1. So we can go that far left, that far right. And then we can also go up or down 0.1, right? Y can be as big as 2.1 and as small as 1.9. So we're looking at this region here. And we're basically saying M, the number that has to go in this calculation, is the upper bound of all the second derivatives evaluated on this region here. So basically the biggest any of those can be on this square or rectangle. Okay, let's find them. So again, here's the function. So let's find fxx, fyy, and the mixed partial. So fxx, well, I should find fx first. Come on, James, be serious. I guess it's on the other side of the board, but whatever. So fx is y, holy smokes, can I write anything? Maybe. It is y squared plus y cosine of x plus pi over 2. And fy we found to be 2xy plus sine of x plus pi over 2. It looks like fxx is going to be 0 plus y times the derivative of this, which is going to be negative sine of x plus pi over 2. So it'd be y times negative sine of x plus pi over 2. It looks like fyy, it's going to be running out of room. Let me just erase this over here. Fyy is going to be the partial of this with respect to y, so it's going to be 2x plus 0, right? Because the derivative of this is 0 with respect to y. And finally, fxy or fyx. So fxy is going to be 2y plus cosine of x plus pi over 2. Okay, so now the question is, in this region where y is between 1.9 and 2.1 and x is between negative 0.1 and positive 0.1, what's the biggest any of these three things could possibly be? Well, let's look at this one first because it looks the easiest to deal with. So since x is at most 0.1, this is going to be less than 0.2. Okay, that doesn't seem very big compared to what we might get here. This one, I feel like you could get this to be as big as, well, I'm going to kind of go with the safe answer here. This could be less than 2 times y. Well, y can be as big as 2.1. That's going to be 4.2. And then cosine of x plus pi over 2. So it really can't get to be as big as 1, but if we want to err on the side of being super careful, you could say it could be almost as big as 1. The reason it can't be as big as 1 is because cosine of 0 is 1. And we are very much, since x is between these two numbers, we're pretty close to cosine of pi over 2, which is actually pretty small. So I bet we could even say this is probably even less than just 4.2 plus 0.8, which is 5. I'm pretty sure that'd be a safe bet. If we really wanted to, we could check cosine of 0.1 plus pi over 2. Let's go ahead and check it. Why not? I'm curious now. Cosine, where'd you go? Cosine of pi over 2 plus 0.1 is negative, oh yeah, because I went to the other side, is negative 0.099. And cosine of pi over 2 minus 0.1 is positive 0.099. So it's not even as big as a tenth. So, I mean, 5 is definitely an overestimate. This value here is way bigger than these two. That's okay. It's okay to overshoot your error estimate usually. So we got fyy is smaller than 0.2. fxx is definitely, so fxy is definitely smaller than 5. And then fxx, the most y could be is 2.1. And the most sine could be is 1. So again, this looks like it's going to be less than 2.1. So it looks like 5 is the upper bound on m. Okay, so then that means our error is less than or equal to 1/2 times 5 times x minus x naught. Where did the x and the y come from? Let me double check what that is. Oh, it's at the point we're looking at. So, sorry. Oh, I guess it's just in terms of x and y. Oh, no, I see. Okay. Yeah. Sure. So, right, x minus x naught is less than 0.1, right? That's what we're given. Sorry. Right, because this is our x minus 0 is less than 0.1. So this is going to be 0.1 plus another 0.1 squared. So this is going to end up being, it looks like 5/2 times 0.2 squared, which is 5/2 times 0.04, which is looking like 0.2/2, which is 0.1, which I feel like is a coincidence. Interesting. You could get a different answer, right? If you had said this was a different number, like 5.2, you get a slightly larger answer. You could have even gone smaller, right? You could have said this was like 4.3. It's still been correct. So getting your upper bound for m in this wacky equation is kind of it's a process that has some opportunity for variability in your answers. Someone might get one thing, someone else might get another thing, and still both be correct. Okay. What time is it? It's 2:20. All right, we still got plenty of time to do stuff. I feel like we could. Do you want to see another example of this error stuff, or should I move on to talking about categorizing extrema? I know that's an or question and not like a yes or no question. So, more tangent planes and errors, or extrema? You guys are like, just pick. Okay, someone said something, good enough for me. I think that's probably what I would have decided if no one said anything, because extrema actually are kind of interesting, and also kind of go back to a place we were long ago. The nice thing about classifying extrema is it's a relatively straightforward process, unlike some of the stuff we've been doing. I feel like classifying extrema is a little bit easier to kind of mentally grasp. So let's look at some examples. Let's find and classify all extrema, all relative extrema of the function of two variables, f of x, y equal to 3x cubed plus xy squared minus 9x squared minus x squared. And I should say this process really only works when you have a function of variables x and y. Like you can't have, like it doesn't so much work for something where you've got like a sphere where it's x squared plus y squared plus z squared equal to a number. You really kind of have to have z as a function of y, or be able to isolate z as a function of y, which like for, I guess no, that's really simple, which for some examples just doesn't work. So we got to find the critical points. To find the critical points, you're going to find where both partial derivatives are simultaneously equal to 0, meaning a point that satisfies both fx equal to 0 and fy equal to 0 for the same x and y coordinate. All right, so let's find fx. It's going to be 9x squared plus y squared minus 18x. Is that really right? Yeah, looks good. And solve, so I don't know what to do with that just yet. We find fy. Fy is going to be, let's see, 2xy, 0 minus 2y. Okay, here is the key to finding critical points. Deal with the equation that looks easier first. This equation here, I don't have any higher powers, right? I've just got x to the first, y to the first. This looks relatively straightforward to possibly actually identify some contenders for critical, if not critical points, at least possible critical points, I should say. Candidates. So I'm going to factor. Factor is always a good idea. I got 2y times x minus 1 equals to 0. Okay, so here's what I've got. I've got either, so just to make sure that this partial is equal to 0, I can either say that y is 0, that will certainly work, or that x is equal to 1. But what I really need to stress is that 1, 0 is not a critical point. Yeah, 1, 0 does make this partial derivative equal to 0 in every way possible. But 1, 0, right, if x is 1 and y is 0, that does not satisfy this. Right, if x is 1, you get 9, and y is 0, you get 9 plus 0 minus 18. That's not 0. What we do is we use, these are separate conditions, right? Only one of these things needs to be true for this partial derivative to equal 0. But then we also need this partial derivative to equal 0. So we're going to use each of these conditions and see what we get from that. So let's start with y equal to 0. If y equals 0, then fx is going to equal 9x squared minus 18x, because the y is going to go away. It's going to be 0. We need that to be 0. So I can factor out a 9x. With 9x times x minus 2. So I get, when y equals 0, I get x equals 0. But I also get x equals 2. So far I've identified 2 critical points. I have when x is 0, y is 0. And when x is 2, y is 0. Both of those satisfy both of these equations. If x is 0 and y is 0, clearly this is 0, clearly this is 0. If x is 2 and y is 0, well, if y is 0, clearly this is 0. And if x is 2 and y is 0, you get 9 times 4 plus 0 minus 18 times 2. So 36 minus 36 is 0. But then we also have to check out when x equals 1. So if x equals 1, plug that in here, I get 9 plus y squared minus 18 equals 0. So y squared minus 9 equals 0, y equals plus or minus 3. So I also get the points 1, 3, and 1, negative 3. I should also mention, just because it does come up, let's say for just a second that this equation, instead of plus 18x, instead of minus 18x, was actually plus 18x. If it was a plus there, just for one moment. It wouldn't change anything about this part here. It would change this critical value. Instead of getting 2, 0, you get negative 2, 0, because you would have you'd have a 9x squared plus an 18x. Fine. But over here is where it would actually matter more. Because if this was a plus 18, then you would have y squared plus 27 equal to 0, which wouldn't be solvable. So what I'm trying to point out here is that sometimes some of the equations don't lead to any critical points, right? If this was the equation, if this was 9x squared plus y squared plus 18x, because this was a plus here instead, right? If that was a plus there. When you had x equal to 1, you wouldn't have actually gotten any critical points because there wouldn't have been any y's to go with it. So sometimes finding one partial derivative equal to 0 doesn't actually yield the other one being able to equal 0, and that's okay. Sometimes you don't get any critical points. That can also happen. Not usually, but it does happen. So these are our 4 critical points, 0, 0, 2, 0, 1, 3, and 1, negative 3. And now we want to classify them all. Okay, so to classify them, we have to find the determinant of the Hessian. What? This is something you'll see. It more shows up in the 17th series. Certainly, I imagine most of you, all of you, probably have to take 22A at some point where you'll find determinants of matrices. So there is this matrix of second partial derivatives. It looks like this. So here's the Hessian matrix. Again, this is probably not super important at the moment, but I might as well say it because it's not hard to understand. The Hessian matrix of second partials is fxx. I don't remember which order it goes. I think you're doing one. It doesn't really matter. I mean, it matters a little bit, not a lot. So there's your Hessian partials with respect to x first, and then x and y. So basically, the rows are partials with respect to x first, y first, and the columns are partials with respect to x second, y second. The determinant of this matrix so when you're finding the determinant of a 2 by 2 matrix, it's equal to the product of the diagonal elements minus the product of the off diagonal elements. It's different for larger matrices, but for this matrix, it's fxx, fyy minus fxy times fyx. And since for all the functions we're going to deal with, the mixed partial is the same either way you do it, we typically calculate this as fxx times fyy minus fxy or fyx squared. And then there are 3 possibilities. 4 possibilities? 3 possibilities. One of those has a subcategory possibilities. So possibility 1, this determinant of this Hessian is negative. If that's the case, then you have a saddle. And I'll say more about this in a second. Possibility 2, this determinant is positive. If that's the case, you have 2 sub-possibilities. You have either a maximum if either of the second partials is negative. So remember back in 21A, when we did the second derivative test for a relative extrema, and we said, oh, and the second derivative is positive, it's concave up. You have a minimum. Second derivative is negative, it's concave down. You have a maximum. That is what we are saying right here. If this quantity is positive, then you have a maximum if either fxx or fyy are negative. Right, because the second derivative will be negative, concave down, maximum. And the idea basically is for this quantity to be positive, these things have to have the same sign, right? Because if this is going to be positive, you have to have a positive thing minus a positive thing. For that to turn out to be positive, this part has to be positive, which means these 2 things have to have the same sign. So checking this is the same as checking this and vice versa. The other option is you have a minimum if either of them are negative. Sorry, positive. Apologies. And then lastly, the sad case. If it's equal to 0, we don't know. You might have a min, you might have a max, you might have a saddle, you might have something that's none of the above. It can be super wonky. So if it's equal to 0, more inspection is required. And I'll show you an example of this as well if we have the time. Yeah, we should have the time. Yeah. Okay. So back to the example we were doing. We need to find our second partials. Let's see. I'm going to erase all this and just leave my critical points on the board. So there's my critical points. Let's find our second partials and our mixed partial. So fxx is going to be 18x minus 18. Fyy is going to be 2x minus 2. And fxy, or fyx, so fyx would be 2y. fxy would be 2y. Good, they're the same. Okay. So then let's calculate the determinant of the Hessian. Good old capital D. It's going to be this times this minus this squared. So it's going to be, I might write this as 18 times x minus 1 times It seems like I made a mistake somewhere. No, I guess not. It just feels like I made a mistake, but I guess it didn't. I'm like, why did they both have X's? Okay, I guess they both have X's. That seems slightly funkalicious, but I guess that's what happens sometimes. I can double check. No, that's totally right. Okay. And so this is 2 times x minus 1 minus this quantity squared. Simplifying this just a tiny bit, this is equal to 36 times x minus 1 squared minus 4y squared. And then I have to evaluate this at each of these 4 places. So this determinant at 0, 0 is, let's see, plug in 0, you get 36 times 1 minus 0. So you get 36, which is greater than 0, which means it could be a max or it could be a min. We have to check the second derivative. So if I check my second derivative, my second partial, at 0, 0, it's going to be negative 18. So fxx at 0, 0 is negative 18. Fyy at 0, 0 is also negative, it's negative 2. That means it's going to be concave down, so we have a maximum. Okay, let's look at this determinant at 2, 0. I think we're going to get the same result, or similar result anyway. I plug in 2 for x and 0 for y, I'm going to get 36 again, which means it could be a max, it could be a min. Let's check it out. Let's look at fxx at 2, 0. So plug in 2, 0, it's going to be 36 minus 18, which is going to be positive, which means it's concave up, which means we have a minimum at 2, 0. Let's look at 1, 3. Sorry, D at 1, 3. So plug in 1 for x and 3 for y. I'm going to get 0 minus a positive number, minus 36. And if it's negative, automatically we have a saddle. And then D of 1, negative 3 is going to give us the same result. You're going to get 0 minus 4 times 9, which is going to be negative 36. So you have a saddle. Let me see one thing here. Sorry, no. So basically, the idea with a saddle, like its name suggests, right? I drew a saddle earlier. Right? A saddle is going to be concave up in one direction and concave down in another direction, right? Like this kind of deal here. Right, so that's why it's neither a max nor min, because it's a maximum in one direction and a minimum in another direction. The thing is, the directions might not be the x and the y direction, right? Here, if you look at this point, fxx at this point is 0, and fyy at that point is also 0. So, but there's maybe some, like, instead of being like the x and the y directions where it's concave up and concave down, it might be like rotated 45 degrees or something, and it's concave up this way and it's concave down that way. So there definitely are 2 directions at this point, where one direction is concave down and the other direction is concave up. And they might not be exactly perpendicular to each other. They might be like this or like that or something weird. But whereas for a maximum or a minimum, right, you're basically at a point, if it's a minimum, where no matter what direction you travel in, it's some sort of like bottom of a parabola where it's smaller than everything around it. And if we want, I think we could try graphing this one in 3 dimensions, like actually looking at the graph. Let's find out. Let's see if we can do this or not. Let's see here, where are my graphing tools? Let's see if we can do this. Let's give it a try. So that's not the function I want. Let me grab the function I want, which I know I literally just, sorry, I blew it. I just want to delete you. Okay, go away, go away. Good. Okay, so what have I got here? I've got 3x cubed plus xy squared minus 9x squared minus y squared. Okay, so maybe if we rotate this thing around a little, okay, we can kind of see, look. So yeah, look right there, 0, 0, 0, 0, 0. There's a maximum, right? It's definitely bigger than all the stuff in its immediate vicinity. And I should point out it's a relative maximum. Hopefully you guys are cool with me showing you that. And then over here, which has got to be the point 2, 0, whatever the z value is. And that kind of makes sense if we, again, right, if you look at it, right, that's definitely, yeah, look, you can't see me, I'm not trying to point at it. Look right there. So if you look, right, if you think of this as being the positive x direction, we've definitely gone 2 in the x direction, and then not any in the y direction, and then down to that point right there. You may or may not believe that, but it is really that, yeah. And then our saddle points, I think, are like right here and right over there, right? Where, oops, no. Oh, no, now we're in trouble. Sorry, I've blown it. I've started rotating it in bizarre ways. Right, you can kind of see, I think, right, that it's definitely concave down in this kind of back and forth direction right there, and concave up in this side to side direction there. So definitely, right, that is what is being described by this D calculation. So that's hopefully value added there. That seems kind of neat. The process is sometimes a giant pain, sometimes it's not. So this wasn't too bad, right? We were able to find the things relatively straightforwardly. Let's look at, we got time. Let's look at another example. And then I think we will save Lagrange multipliers for Thursday. For those of you in Bielo's class, when is your final? It's like none of us are in Bielo's class. We don't. Next one's every class I am co-classing for, my 17B class, both of the 16As that have a midterm, that have a final, and this class, all the finals are on Wednesday. That's interesting. Okay, I will. I'll try and look, but if there's any like practice final or final study materials that he's given you guys, if you could possibly send it my way, I would love to have that just so I can kind of figure out what to come up with for you guys for next week. For the Waldron folks, if there's anything you want to know or see before then, please don't hesitate to ask. But since you guys don't have a final, I will probably focus more on the BLO folks. Unless there's something you really, really need to see, which I'm happy to talk about. Well, let's look at another example here. Let's look at this function of 2 variables, which is, let's see, 2x to the 4th minus 4xy plus y squared. And we're going to do the same thing. We're going to find and classify the critical values. I should really say critical points, right? They're not critical values, because in 21A, critical value is the one x value that you find to see where the derivative is positive. Here we're finding the point x and y coordinate that is a critical point. Okay, so partial with respect to x, 8x cubed minus 4y. Partial with respect to y, negative 4x plus 2y. And again, it is usually in our best interest to try to deal with the one that looks simpler, preferably the one that has less awful powers. So I'm going to deal with this one now. Here's the thing. There's a lot of points to satisfy that equation, literally an infinite number of points. Right, 0, 0, 1, 2, 2, 4, pi, 2 pi, right? So the thing is, we just have to write y as an equation of x, or x as an equation of y. Either way, I'm probably going to do y in terms of x. 1, because that's typical. 2, because if I have to sub back into this other equation, I'd rather sub into the thing that's less complicated to deal with. So I'm going to say 2y equals 4x, y equals 2x. And then that is going to go back in there. So this is going to become 8x cubed minus 4 times 2x equal to 0. So let's see, I've got 8x cubed minus 8x equal to 0. Factoring is our friend. 8x times x squared minus 1 equal to 0. So x equals 0 or plus or minus 1. And then we go back over here and we say, okay, well, if x is 0, then y is 0. If x is 1, then y is 2. If x is negative 1, then y is negative 2. So we found our 3 critical points. And you can check if you want that each of these 3 points simultaneously solves each of these equations. Plug in 0, 0, that's clearly 0, that's clearly 0. If you plug in 1, 2, 8 minus 8, 0, negative 4 plus 4, 0. Plug in negative 1, negative 2, negative 8 plus 8, 0, positive 4 minus 4 is 0. So that's kind of the idea, is you're always saying, okay, I'm going to try and work with one of these. Sometimes you're not going to really get a whole lot, right? You're just going to be like, well, I've got a relationship. And then you can plug that back in there and try and actually find something. And then you can use those. So you're kind of always going back and forth between the 2 equations. You solve one equation, you get something. Plug it into the other one. Try and solve them. Get some numbers. Plug those back into the other one so you can find the corresponding other coordinate. Okay, so now let's find the partials. I should say the second partials. So fxx is 24x squared. Fyy is 2. And I can do fxy or fyx. Either way, it's going to be negative 4. So my capital D, my determinant of my Hessian, is this times this, so 48x squared minus this squared. Okay, this is very easy to calculate. So let's see what we've got here. At 0, 0, we're going to get negative 16, which means we have a saddle point. At 1, 2, we're going to get 48 minus 16, which is positive 32. And since it's positive, so again, it's really kind of easy to get into the, to get a little bit not careful with this particular quantity here. When your determinant of your Hessian is positive, right, you have to do more. You can't just say, oh, it's a max. What's it? You have to say, oh, it's either a max or a min. And then you have to look at the concavity. Now, here, Fyy is clearly always positive. So is Fxx if you really want to get fancy about it. I guess it's not always positive, right? It could be 0 when x is 0. Okay, fine. But Fyy is always positive. So if you have a max or a min, it's clearly concave up, which means we clearly have a minimum. So we have a minimum at 1, 2. And I think we're also going to have a minimum at negative 1, negative 2. Because we plug in negative 1, negative 2, you're still going to get 48 minus 16, which is still positive, which means you have a max or a min. The second derivative hasn't changed. It's still concave up. You still have a minimum. And just because I think it's kind of fun to see. So I do, if you're at all interested, I do think it's worthwhile to graph these things in the 3D graphing thing, which if you don't have the link, right, you can just Google like 3D graphing Desmos and you'll find this. I'm sorry, I sent that just to one person. There we go. But if you want, right, we can graph this one as well. It just, I think it's neat and maybe it's helpful to kind of look at these things and be like, oh, that's really what's going on there. So I want to graph this one, which I'm pretty sure is just a rotated saddle, kind of. 2x to the 4th minus 4xy plus y squared. Oops, not equals, minus. So looking at this monkey beast here, you can definitely see, oh, look, yeah, there's your 2 minimums, obviously. And right in the middle there, you can kind of see the saddle, and kind of is maybe a stretch there. If you rotate it this way, whoa, oh my God. So, I mean, clearly this does have some limitations, and it's not perfect, but you can kind of see the saddle-esqueness there, maybe a little bit better this way, right? It's kind of going down that way, up this way. So anyway, I feel like rotating this way never really accomplishes anything useful. But you can rotate this way, you're like, oh yeah, there's my. I want that one. Yeah, it's kind of interesting. You can't really see anything there. Anyway, I should stop playing around with this because it's not really the point. So, okay, sorry, I'm stop sharing. So I think I had one more problem I wanted to make sure I did. Yeah. Oh yeah. So can I fit 2 more problems in? Maybe. So let's look at this next one, because this one's kind of interesting. It's easy if you think about it. It's hard if you don't. I mean, I guess that's probably true, or at least it's always going to be hard if you don't think about the problem. It might be easy. So let's look at this function. F of xy equal to, what do we got here? X squared plus times y to the 4th. Another example would be g of xy equal to x to the 4th plus y to the 4th. These are 2 pretty common examples. So let's find the partials. Fx is 2x y to the 4th. Fy is x squared times 4y cubed. And I think we can see that the only way you're going to get that either of these is equal to 0 is if both x and y are equal to 0. Both? Do we need both? That's an interesting thought. So this equal to 0. Oh, I made it. No, I'm not crazy. I feel like there's actually maybe a lot of critical values here. Maybe this isn't a great example. What do I mean? Well, if you look here, I think 0, 1 is a critical point. Is 0, 1 a critical point? First derivative here is definitely 0. Oh yeah, this one like, I think you have like a whole like, I think the entire x-axis and the entire y-axis are all critical points. It's kind of weird. Let's leave this example behind for a minute. Maybe we'll come back to this one on Thursday. This example is actually a better example. So here you only get 1 critical point. The partial with respect to x is 4x cubed. If you set that equal to 0, you're only going to get x equal to 0. Similarly, gy is 4y cubed. Set that equal to 0, and you only get the point 0, 0. Whereas here, you get 0, comma anything, and anything, comma 0 are all critical points, which is a little bit stranger. Yeah, I'm gonna have to look at this one later. I think it's yeah. All right, sorry, I'm getting all kind of caught up with this one. You should graph this one on your own sometime using the link I just sent you guys. I think the graph of this is kind of neat. Anyway, here our critical point is 0, 0. But then if we find the second partial here is 12x squared. Second partial here is 12y squared. Mixed partial is definitely 0. And if we find d is 12x squared times 12y squared, which is 144 x squared y squared minus 0. And if you plug in the point 0, 0, you're going to get 0, which is inconclusive. So how do we know if it's a max or a min or neither? Well, I mean, do we have to? I guess we don't have to, but you can definitely determine that this one's a maximum because, well, I mean, it's x to the 4th plus y to the 4th. X to the 4th is always greater than or equal to 0. Y to the 4th is always greater than or equal to 0. So no matter what, we know that x to the 4th plus y to the 4th is for sure greater than or equal to 0. Well, when you plug in 0, 0, you get 0. So it's the smallest thing around. So we definitely have a minimum at 0, 0. Even though this test was inconclusive.